Hello everyone, I am Komal Shantaram Tamboli, pursuing Masters in Data Science from Liverpool John Moores University in December 2024. Today, I will be representing my thesis topic, which is Gems and Numbers Unveiling Diamond Price Trends and Analysis. Today, I will take you through the fascinating world of diamond price prediction, starting with an exploration of its background. Then, we will delve into historical research to understand the trends and insights that have shaped this field. In problem statement, we will tackle the challenges that have arisen in this domain and explore the methodologies used to address these. Finally, we will discuss the results and conclusions drawn from our work while also suggesting potential areas for future research and development. Diamonds are one of the most valuable and desired gemstones created deep inside the earth under high heat and pressure over millions of years. They are mainly judged by the forces, that is, carat, cut, color, and clarity. Diamonds have always been symbols of luxury, wealth, and strength. The price of diamonds can change due to factors like supply, demand, economy, and new market trends. The diamond industry is characterized by high variability in pricing due to factors like diamond quality, rarity, and market demand. Let me tell you the traditional way to calculate diamond price as price per carat into carat weight into cut adjustment into color adjustment into clarity adjustment. But cut, color, clarity can differ based on a grading system, and that certification given by Gemological Institute of America, that is GIA and AGS, along with market trends. Let me discuss with you historical research has established in this domain. In 2001, Chu developed a multiple linear regression model to predict diamond prices using key factors such as clarity, color, and carat as the basis for forecasting. After a decade, in 2010, Scott and Elovitz examined the forces to calculate the logarithmic value of diamond prices. However, due to the complex nonlinear relationships between diamond attributes and their price, the research could have been further enhanced by incorporating machine learning algorithms. In 2018, couple of research has established, as per Stansel, he began conducting an exploratory data analysis and then expanded the predictive modeling process to include a range of powerful data mining techniques. These included multiple linear regression, decision forest, boosted regression tree, and artificial neural networks, all of which were designed to capture the complex nonlinear relationships between the predictor variables and diamond prices. Again, in the same year, Pena evaluated three linear algorithms combining regression, neural networks, and MFIP to predict diamond prices. Again, in 2019, Fitayanon implemented five machine learning models, including the generalized linear model, decision tree, random forest, and gradient boosted trees, alongside one deep learning model, the nonlinear autoregressive with external input model. In the same year, A.C. Pandey explored multiple assembles method and compared their performance to determine the most effective approach. To further enhance the algorithm's efficiency, future selection techniques like PCA, recursive feature extraction, and chi-squared were also applied. After, in 2020, Al-Surahi utilized a variety of regression models including linear regression, random forest, polynomial regression, gradient descent, and neural networks to enhance the prediction process. In early 2021, Harshavardhan Mihir applied a range of machine learning algorithms and also developed a user-friendly graphic user interface that utilized OCR technology to read diamond certificates. Thereafter, Thanapon developed both ML and DL models, fine-tuning various hyperparameters such as activation functions, learning rates, batch sizes, and the number of epochs. To optimize these settings, they used grid search cross-validation. Thereafter, Shafi Lahar used KNN and Lasso machine learning algorithms to predict diamond prices. The approach included choosing key features and fine-tuning the value of K for KNN and alpha for Lasso to enhance prediction accuracy. In 2023, several researchers leveraged regression classification methods, ELM, Weka tools, and M5P models to predict diamond prices and exploring different approaches to enhance accuracy. In 2024, many researchers employed a range of ML and DL models to develop accurate price prediction systems and compared their results to identify the most effective approaches. Let's discuss the problems that have arisen in this domain. Firstly, the traditional method of calculating diamond price faces challenges such as subjectivity in grading, marketing fluctuations, and reliance on incomplete data. These issues can make pricing inconsistent, difficult to predict, and hard for both buyers and sellers to navigate accurately. In addition, while deep learning can offer powerful predictions for diamond prices by capturing complex nonlinear relationships, challenges such as a limited and inconsistent data, market volatility, computational cost, interpretability, and overfitting must be carefully addressed. Overcoming these challenges requires high quality, real time data, expert feature engineering, robust model evolution, and ongoing model refinement. Thirdly, machine learning models have demonstrated proficiency in predicting diamond prices, but the real challenge lies in extracting precise parameter values from blurry diamond certificate image using OCR techniques. Lastly, diamond price prediction is significantly affected by overfitting and underfitting models. Overfitting models are too complex, capturing noise in the data and failing to generalize new diamonds. In contrast, underfitting models are too simple, neglecting crucial factors that impact diamond prices. This leads to failure to capture the underlying connections between diamond features and prices, resulting in inaccurate predictions. Let me discuss with you methodology that we are using. We are taking the dataset from Kaggle contains 53,940 unique rows, including elements such as carat, cut, color, clarity, depth, table, price, length, width, and height. Then we are moving in data preprocessing. In the dataset, cut, color, and clarity are categorical variables, meaning they represent qualities that can't be directly used by machine learning models. To make them usable, label encoding was applied, converting each category into unique number. This transformation allows the data to be processed by the models. Second, it is observed that Some records in the diamond dataset have zero values for length, width, and height, which means they might represent diamonds with missing dimensions. To maintain the quality and accuracy of the data, we removed these rows. In the dataset, there was an index column. When pandas read the data, it automatically created an index, which caused the unnamed zero column to be dropped. The next step is exploratory data analysis. EDA is a critical step in the implementation of diamond price prediction model. It involves visually and statistically analyzing the dataset to understand its underlying structure, identify patterns, detect anomalies, and gain insights that guide further steps in model development. In figure 1, the distribution of the carat feature isn't always even or normal. In diamond dataset, it often shows a right skewed pattern, meaning there are small diamonds than larger ones. Figure 2 is the carat versus price. It appears that the price increases exponentially with the carat weight. As we can see that in figure 3, the ideal cut is the most desirable, whereas the fair cut tends to have comparatively lower demand. The figure 4 is color versus count. The nearly colorless G diamond is in a higher demand compared to the J color diamond. Diamonds with color grades D, E and F are colorless, while diamonds with grades G, H, I and J are near colorless. The violin graph shows that diamonds with D and E color grade tend to have a high median price, with prices clustering closely together. On the other hand, diamonds with J and I grade have a wider price range, including some cheaper diamonds. In figure 6, we can see that diamonds with a premium cut have a higher median price compared to diamonds with a fair cut, indicating that better cuts typically command higher prices. Let's talk about clarity versus price. Diamonds with Si1 clarity have a much higher median price than diamonds with VVSR S1 clarity. It highlights the significant price difference based on clarity. Diamonds with VS1 and VS2 clarity have a wider price range, indicating that their prices vary more depending on other factors like carat, color, or shape, while diamonds with IF clarity may have more consistent pricing. Figure 8 shows diamonds volume. A right-skewed histogram indicated that while there are many small diamonds, there are also a few larger diamonds that are much rarer and more expensive, contributing to a higher overall value in the market. Next step is a feature extraction. The diamond's volume was calculated by multiplying the length, width, and height of the diamond. Along with the diamond volume, we considered cut, color, clarity, carat, price, features. Now let's talk about the model selection. Model selection is to identify the most accurate and efficient model for predicting diamond prices. Several models were considered, including linear regression, lasso, AdaBoost, Reach, Gradient Boost, Random Forest, KNN, which help improve the prediction accuracy. Now, next step is model training. In the linear regression, we performed eightfold cross-validation, where the data was split into 8 subsets. The model was trained on 7 of those subsets and tested on the remaining one. With this process repeated 8 times, each time using a different subset as the test set. This resulted in better model performance, though it increased computation time. Now let's talk about the lasso. Lasso created a sparse model by reducing the number of features used for prediction, resulting in a simpler and more interpretable final model. By setting alpha to 0.1, a small regularization effect was introduced, encouraging some degree of coefficient shrinkage without overly simplifying the model. The evaluation metric during cross-validation was declared, which helped assess the model's performance and guide the selection of hyperparameters that led to the best model performance. KNN KNN improved diamond price prediction by offering a flexible, non-linear model that made predictions based on the similarity between data points. Setting 5 neighbors allowed the KNN model to generalize well to unseen data. If numbers of neighbors had been too small, like 1, the model might have overfitted the training data and performed poorly on new data. On the other hand, if it had been too large, like 50, the model might have underfitted by losing sensitivity to important local patterns. AdaBoost AdaBoost regressor model iteratively refines its predictions and handled complex nonlinear relationships, outliers, and feature interactions, which makes it a strong candidate for diamond price prediction. Setting number of trees to 5,000 and learning rate to too late to faster learning but with a higher risk of overfitting. This resulted in a model that performed well on the training data but did not generalize as effectively to new data. Therefore, number of trees setting to 10,000 and using a smaller learning rate of 1 provided a more stable and generalizable model, though it took longer to train and required more computational resources. Ridge Ridge regression is a linear regression technique that includes an L2 regularization terms to prevent overfitting, especially when there are many features highly correlated. Here, grid search CV was used to find the optimal alpha value by testing a range of values and evaluating the model's performance with each. This resulted in a better model that generalized well to new, unseen data. The alpha of 0.01 is the optimal choice among the different values tested in a grid search CV. Gradient boosting predicted diamond prices by constructing an ensemble of decision trees sequentially, where each new tree corrected with the errors of the previous one. With 1,000 estimators, the model had sufficient opportunity to adjust errors and enhance performance. A learning rate of zero point 0.1 provided a balanced approach. It was not too aggressive or not so small that the model required an impractically large number of trees. This helped the model generalize better to unseen data by setting the max depth to 1. The model remained simple and avoided overfitting by not relying on overly specific patterns. Last model is random forest regression. In random forest regression, multiple decision trees made the predictions. Using 1,000 trees allowed the model to benefit from averaging the predictions of many trees. This reduced variance and helped the model generalize better to new data. More trees gave the model more chances to fix errors and improve its predictions. Setting max depth to 10 controlled how complex each tree could be. Limiting the depth prevented the trees from overfitting the training data by focusing on irrelevant details. It made sure the trees were deep enough to capture important patterns but shallow enough to avoid memorizing the noise in the data. Setting random state to 42 ensured the results were reproducible. The next step is model evaluation. Evaluated each model's performance using appropriate matrices such as mean square error, mean absolute error, and R squared, comparing how well each algorithm predicted the diamond prices on unseen data. The last step is best model. Among all other models, Random Forest is the top performing model. Now it's time to delve into results and discussion. As per the chart, Random Forest and KNN offered the best performance in terms of MSE, MAE, R square because of their ability to model complex nonlinear relationships and their ensembles nature. Adabus performed well with nonlinear relationships and adjusted the model iteratively, resulting in lower error metrics. KNN's performance heavily depend on the choice of K and struggled to scale with large or high dimensional datasets. Linear regression and ridge regression were simpler models that performed reasonably well in linear scenarios, but did not capture complex patterns as effectively as tree-based algorithms. Based on the approach we used, we have drawn several key conclusions and are also proposing potential areas for future exploration. Let's talk about the conclusion. Random Forest and KNN emerged as the top performing models, demonstrating strong predictive power by effectively capturing complex relationships in the data. These ensemble models outperformed simpler methods like linear regression, ridge, lasso, AdaBoost, and gradient boosting, although useful for providing insights and interpretability, but did not achieve the same level of accuracy. The study suggests developing an online interactive platform where users can input diamond attributes and the model will generate the most accurate category, which is a crucial factor in determining diamond prices. Exploring deep learning techniques such as neural networks can improve predictive accuracy by identifying nonlinear relationships and intricate patterns in the data that traditional models may miss. However, deep learning requires real time and large volume of data to be effective. Thank you.